The Suzuki coupling, or Suzuki-Miyaura reaction, is a powerful palladium-catalyzed cross-coupling reaction used to form carbon-carbon bonds between organoboronic acids, or esters, and aryl, or vinyl halides/triflates. It is widely used in pharmaceuticals and materials science due to its mild conditions, high functional group tolerance, and low toxicity byproducts. Reagents. Suzuki coupling requires an organoboron compound, an organic halide or triflate, a base, for example, sodium carbonate, potassium phosphate, and a palladium catalyst. Palladium-catalyzed Suzuki cross-coupling reactions are amongst the most powerful and most applicable methods for carbon-carbon bond formation. The reaction is generally carried out at temperatures range of 60 to 80 degrees Celsius with generally excellent yield results. Despite the availability of other cross-coupling reaction like the Heck reaction, Stiller reaction, to name a few, due to various conditions like 1. Milder reaction conditions. 2. Commercial availability of the diverse boronic acid derivatives that are environmentally safer than the other organometallic reagents. 3. The handling and removal of boron-containing byproducts is easier compared to other organometallic reagents, especially in the case of large-scale synthesis of a product. The Suzuki cross-coupling reaction has an edge over the other cross-coupling reactions, as this reaction is not only restricted to simple compounds, but is frequently used in the production of complex compounds. Mechanism of the Suzuki reaction. Transition metals can activate various organic compounds and, through this activation, catalyze the formation of new bonds. Palladium was the first known transition metal used in organic synthesis, which can induce the formation of carbon-carbon bonds, because ethylene was oxidized to acetaldehyde by air in a palladium-catalyzed reaction, and this became the industrially important Wacker process. Subsequent research on palladium-catalyzed carbonylation led to newer reactions for the formation of carbon-carbon bonds. The principal mechanism of palladium-catalyzed cross-couplings is that two molecules are adsorbed on the metal via the formation of metal-carbon bonds. In this way, the carbon atoms bound to palladium are brought very close to one another. In the next step, they couple to one another, and this leads to the formation of a new carbon-carbon single bond. There are two types of cross-coupling reactions, according to this principle, that have become important in organic synthesis. Both reactions are catalyzed by zero-valent palladium, and both reactions employ an organohalide Rx, or analogous compound, as the electrophilic coupling partner. However, the nucleophilic coupling partner differs in the two reactions. In the first type of reaction, it is an olefin, whereas in the second type of reaction, it is an organometallic compound R''M. A common feature of the two types of cross-couplings is that the organic groups from the reagents are assembled on palladium. Furthermore, both reactions begin by generating an organopalladium complex, RPDX, from the reaction of the organic halide with PD0. The organopalladium species, RPDX, will subsequently react with the nucleophilic coupling partner. The reactions are very mild since they utilize organic halides, or analogous compounds, and olefins, or organometallic compounds, R''M, of low reactivity, where M is typically zinc, boron, or tin. The catalytic cycle involves three main steps. Oxidative addition. The first step of which is the oxidative addition of palladium to the alkyl halide to form an organopalladium species. A palladium-0 catalyst inserts into the carbon-halogen bond of the organohalide R1X, forming a palladium-2, PD2 intermediate. Transmetallation. Transmetallation involves the transfer of ligands, usually carbon-based, between two different metal centers. In the presence of a base, the organoboron compound transfers its organic group R2 to the PD2 complex. Reductive elimination, the desired product is then obtained by reductive elimination, and the catalyst, palladium, is restored. The two organic groups R1 and R2 bond together, releasing the coupled product and regenerating the PD0 catalyst. Suzuki coupling reaction shows excellent functional group compatibility, readily available reagents, and water-tolerant conditions, making it ideal for creating complex conjugated systems like biphenyls and styrenes. The Suzuki coupling reaction is different from other coupling reactions in that it can be run in biphasic, organic water, water only, or no solvent. This increased the scope of coupling reactions as a variety of water-soluble bases, catalyst systems, and reagents could be used without concern over their solubility in organic solvents. Use of water as a solvent system is also attractive because of the economic and safety advantages. The Suzuki-Miyaura reaction is essential for synthesizing pharmaceuticals, for example, valsartan, montelukast, and in the synthesis of polymers and liquid crystals. The first ever application of Suzuki cross-coupling reaction in natural product synthesis was reported in the year 1981 by Rossi and his co-workers, in which an insect pheromone isolated from Diperopsis castanea was synthesized. It has been extensively utilized in the synthesis of many carbon molecules, including the most complex ones. It also finds application in the synthesis of compounds of biological sources, like adragmacidin F, flurbiprofen, felbinac, fenbufen, diflunisal, aporphenoids, nemertyline, gymnosin A, palitoxin, macalamine, halenaquinone, brevetoxin, uechucini, caparatriene, etc., which have been synthesized using the same reaction, along with some other organic compounds. Flurbiprofen is a commercially available non-steroidal anti-inflammatory and analgesic drug, which is used extensively to treat the inflammation and pain of arthritis, has been successfully synthesized using the Suzuki cross-coupling reaction by using palladium charcoal in water. Felbinac, also known as biphenylacetic acid, is a topical medicine belonging to the family of NSAIDs, which is used to treat muscle inflammation and arthritis, has also been successfully synthesized using cross-coupling reaction. Fenbufen, another NSAID that is extensively used in the treatment of inflammation in osteoarthritis, ankylosing spondylitis, and tendinitis, which is also used to relieve backaches, sprains, and fractures, has also been synthesized using the Suzuki cross-coupling reaction. Limitations. While highly versatile, some reactions can be slow, with sterically hindered substrates or less reactive aryl chlorides. Suzuki cross-coupling reaction is the premier industrial method for carbon-carbon bond formation, which is a highly useful and versatile method needed for the development of modern drug discovery and in the synthesis of many natural products, polymers, agrochemicals, and other organic compounds due to its high scalability and functional group tolerance. Although the method has found many applications in synthesizing many different molecules, there is still much work to do on the development of an efficient catalyst applicable to structurally different substrates.